When dealing with curved mirrors, we know that we can draw ray diagrams to locate the image and see some things about the image size and orientation, as well as whether it's a real or virtual image. But there's also equations that we can use to tell us more specifics about the image, things about where the image is located or how big it actually is. Our first equation that we'll use rather frequently is often called the mirror equation. And it tells us that 1 divided by the focal length is equal to 1 over the object distance plus 1 over the image distance. The biggest thing to remember about this equation is the fact that this equation isn't for the focal length, for example, for 1 over the focal length. Each distance in this case is 1 over the quantity. So be very careful when solving for either focal length, image distance, or object distance to note that this equation, when rearranged, will still quite often give you 1 over the distance. And so in the end, you'll have to take your quantity raised to the -1 power. A couple of other equations that we quite commonly use with mirrors are magnification equations. Magnification refers to how much bigger or how much smaller our image is than our object. Note that in physics, the term magnified or magnification refers to an image being bigger or smaller than the object, whereas in our everyday lives, we typically only think of magnification when something becomes bigger. There are 2 equations we can use to calculate magnification. In one case, the equation or the quantity magnification is equal to -q over p, or the negative image distance divided by the object distance. In another value, or another way of calculating it, we can say that the magnification is equal to the image height, hi, divided by the object height, ho. Sometimes we may even set these 2 equations equal to each other to find the image height when we know the image and object distance. Now, there are some sign conventions that are really important to know when using these equations. For starters, the focal length is positive for a concave mirror and negative for a convex mirror. This comes from the fact that the focal point is on the same side as the object for a concave mirror and on the opposite side of the object for a convex mirror. Another sign convention is that the image distance, q, is positive for real images and negative for virtual images. Similar to focal length, this comes from the fact that a real image is on the same side of our mirror as our object, and a virtual image is on the opposite side of the mirror as our object. Lastly, the image height, hi, is positive if the image is upright and negative if the image is inverted. We will, of course, practice with these equations, but the biggest thing that I want to point out with any and all of these equations is it's really important to make sure that your units match. So if your focal length is in centimeters, make sure that your object distance and image distance are in centimeters. I'll also point out the magnification. Since you're dividing centimeters by centimeters or meters by meters, magnification has no units.